All right, so a couple of ground rules. I know for those of you who've been here before, you know this. When these ladies are done, we're going to take them out the back door and they will do a Q&A in the hallway. If you come and approach the stage, bad stuff will happen. Probably not to you, but more to me, because I'll get in trouble. So everyone goes out. See those podiums back there? Yes, I see the podiums back there. Yes? Say yes, everyone? Yes. Okay. Please go out that way, because they're going to start loading the room for the next talk. So with that, I will leave it to these lovely ladies.
No seat, no talk.
No seat, no talk?
Right. They have to have a seat, they can't be in them.
Okay. So for those of you that are not in seats, sit in them. Now, go, run.
Okay, thanks for the introduction, and I'll need to move this a little. Hi everyone, good morning, and thanks for coming and waking up early. It was hard for me, but we made it. So I'm Aylin Caliskan, and I used to be Rachel's PhD student, but I just started as a professor, and this is my first talk as a professor, so it's very exciting for me. I'll go over the first half set of slides, and after that Rachel will continue with her new findings in our research. And today we'll be talking about how we can de-anonymize programmers based on their coding style. Stylometry. Stylometry is the study of language, study of style in language. And when we say language, we mostly think about natural language, which is, for example, English that we speak or our native languages. But there are also artificial languages. For example, programming languages are artificial languages. And when we say stylometry, we wanted to look at all kinds of languages. And on the natural language side, we have been looking at English or English as a second language to identify the native language of a speaker, or translated text, so that we can again identify the native language or the translator that has been used, as well as the author. And we have been looking at underground forum text, where underground forum users engage in business transactions and so on. And we're still able to identify the authors from their messages. And in artificial languages, we wanted to see if coding style is unique for each programmer, so that it becomes a fingerprint for them. And we have been focusing on Python as well as C and C++. And we have looked at source code, and we saw that there's very high accuracy in de-anonymizing programmers for source code, so we wanted to see if we can do this with binaries as well. And this work, the tools that we have developed and made open source, are being used by many researchers or different agencies as well, such as the FBI or expert witnesses. They can use this scientific information in court while testifying. And European high-tech crime units are using this to, for example, identify suspects in different online platforms. And regarding artificial languages, focusing on code, DARPA is interested in this project, as you might imagine, since they are part of Department of Defense and they might want to know the identities of malicious actors, as well as expert witnesses, and the US Army Research Laboratory, which we are collaborating with, and this has been an ongoing collaboration for 4 years now. Okay, why would we like to de-anonymize programmers? First of all, it's out of scientific curiosity. I would like to know, since we learn programming on an individual basis, do we end up developing a unique coding style? And this can be used for software forensics or detecting plagiarism, but at the same time we can use this, for example, verification of authorship, or this can aid in copyright investigations. But at the same time, such, for example, security enhancing technologies can be very privacy infringing, and it can be used at the same time for surveillance and to track some programmers. Saif Malikpour is one example where we can see security enhancing technologies can at the same time be very privacy infringing. Saif Malikpour, he's an Iranian citizen, and he was identified as the web programmer of a porn site. And when he went to Iran, he was arrested and he was sentenced to death. And he has been in prison for years now, and he couldn't get out, even though he's a Canadian resident, just because he was identified as the programmer of this site that is against Iranian government's views. Okay, how can we use source code stylometry from a machine learning perspective? I'll try to go not into too many details, but try to give you the basics about machine learning so that you understand the flow of how we can de-anonymize programmers. And we're looking at different tests such as multi-class or two-class machine learning tests where we can, for example, do software forensics, plagiarism detection, copyright investigations in two-party cases, as well as authorship verification, which would be a one-class to open-world machine learning test. And in order to do this, we have the traditional machine learning workflow, where first of all, we need training data that is representative of what we're looking for. And then with this training data, we extract some features that are representative of coding properties or coding style. And we feed these features into a machine learning classifier so that we can train the classifier to learn each author's coding style from the features that we extracted. And after that, take the test samples and use the machine learning classifier to identify who this source code sample or binary or text sample belongs to. And in this case, we are using random forest because by nature they are multi-class classifiers and they don't tend to overfit. And when we use this classic machine learning workflow, we see that we get very high accuracies in de-anonymizing programmers, which is showing that if programmers would like to remain anonymous, this is a serious threat to their anonymity if they want to, for example, contribute to open source repositories and they would still like to remain anonymous. And for example, with large-scale de-anonymization of 1,600 programmers, each with 9 source code samples that are on average 70 lines of code, we get 94% accuracy in de-anonymizing or identifying the authors of 14,400 code samples. And in order to do this, we need to develop a method. And while we are first developing the method, we need a controlled environment to do this. And for that, we chose Google CodeGem as our development data set. Google CodeGem is an annual competition where contestants from all over the world try to solve algorithmic questions within a limited amount of time. And as they are able to provide their solutions, correct solutions, they get posted online, Google posts them, and they go to higher rounds where programs become, or the problem becomes harder, and they have to implement more sophisticated functionality so that we can control for the difficulty of the problem as well as how advanced the programmer is. Okay, we have our data set and we collected source code samples from 1,600 programmers, and we pre-process the code samples, especially to get the abstract syntax trees from source code. And for that, we use a fuzzy abstract syntax tree parser, which is able to even parse incomplete source code. And with the abstract syntax tree that represents the grammatical structure of code, we start extracting features, feed it into a random forest, and each tree of these 500 trees in the random forest are voting for one particular programmer as the most likely programmer to have written a particular disputed test sample, and then we do classification. And when we're talking about features, we look at different categories of features. For example, when we look at the source code sample on the left side, we see how function names or variable names are chosen by programmers, and these are higher level features that can be more easily changed, and they're called lexical features. And spaces or the formatting is also part of these lexical features. But there are also syntactic features, such as the grammar of natural language. In this case, this is the syntax, the properties of this programming language. And when we get the abstract syntax tree, we can see how complicated this structure can get. And based on this, we extract features such as, from the lexical side, things such as variable names, function names, spacing, bigrams, or features like this. But on the abstract syntax tree side, we are looking at more structured features, and we abstract things from about 50 different abstract syntax tree nodes, such as function and statement, 2 nodes that are connected to each other with an edge. And then how the average depth of a node is, for example. And these are very identifying features, and they are not as trivial to change quickly. And how can we use these in real-world scenarios? Okay, we extract these features and let's try to see how we can represent or replicate real-world cases. Let's say that we would like to find out who Satoshi Nakamoto is. And let's say that we have a suspect set of size X. We take the suspect set's source code samples from the past so that we can train classifiers with this training data from the suspect set, extract features, and then take Bitcoin's initial Git code as the test sample, and then try to see which programmer is most likely the author of Bitcoin's first Git commit. And when we try to replicate this scenario, take 1600 programmers from Google Code Jam, though this is not a suspect set. With these 1600 programmers, we use 9 files for each of them, and then we get 94% accuracy in correctly identifying these, and we use 9-fold cross-validation for this. What happens if a programmer would like to stay anonymous and knows that coding style would give them away? Obfuscation is the first thing that comes to my mind, and off-the-shelf obfuscators such as Stylistic, and it's available online, many programmers use it. And when we take it to obfuscate our code, here we see the original sample, and we can see different spacing or formatting with a certain abstract syntax tree structure, as well as different function and variable names. And once it is obfuscated, all the function names or lexical features are refactored with random representations, and all the commands are replaced with hexadecimal ASCII representations. So everything is refactored, spaces are stripped, and so on. But we see that the de-anonymization accuracy is not affected by such obfuscations at all, because when we look at how the obfuscation happened, we see that refactoring did not change that abstract syntax tree at all, and it remains unchanged. So our method is impervious to such off-the-shelf obfuscators. Okay, what happens when we use more sophisticated obfuscators such as Tigris? I take about 15 lines of code and obfuscate it with this function virtualizer, and then I end up with about 500 lines of code. It looks much more cryptic, and I cannot really tell what's going on easily from a higher level. And at the same time, the abstract syntax tree, most importantly, changes in this case. Okay, and this affects accuracy significantly. So the accuracy of being able to identify C programmers was 96% for 20 programmers. And here the random chance of correctly identifying a programmer is 5%. When we obfuscate it with Tigris, the accuracy drops down to 67%. Okay, there's a significant drop in accuracy, but compared to 5% of random chance, 67% is still a high threat to anonymity, even when we obfuscate it with such sophisticated obfuscators. And another case, another real-world case would be authorship verification. For example, someone comes up and says that, okay, I'm Satoshi Nakamoto, and in that case, we can ask for their past coding samples, take those samples to train a classifier where this person, Satoshi or Mallory, is one class, and then the second class is the open world. It's programmers, random programmers from the open world. And then I take Bitcoin source code and try to see who it belongs to. Does it belong to Mallory or to the open world? And based on this, we can see if it belongs to this Mallory person, and at the same time, if we have training data from this person in the past in different open world scenarios. Okay, what about executable binaries though? When we compile code, it goes through various transformations. Does coding style remain in compiled code? And again, we have a few lines of code, and in binary it looks quite cryptic. We cannot tell much, but thanks to improvements in reverse engineering methods, we can generate rich feature sets even from binaries. And in this case, we know that malware authors would like to remain anonymous and do not have any identifying information out there in the public. And there was this fun interview with the law about malware author, and this used to be recent, but it's 2016 September, it's not recent anymore. But when this author is asked, who are you? The answer is just some guy who likes programming. I'm not known security researcher, programmer, or member of any hack group, so probably best answer for this would be nobody. Malware authors, or people that would like to remain anonymous, would like to be nobodies, but if in binaries, coding style is embedded, then that shows that that is a fingerprint identifying information for certain users online. Okay, again, we have our classical machine learning workflow. We need source code samples for a controlled environment, which we take from Google Code Jam, compile it, and then reverse engineer it to get disassembly features, decompile it to get the source code so that we can extract or generate the abstract syntax tree as well as the control flow graph. And then for 100 programmers, we are left with about 1 million features. So with 1 million features, I cannot really tell what's going on about style of these programmers. So we apply attribute selection methods to select the features that are most representative of style in binaries. And then feed this again into a random forest of 500 trees and then do classification to de-anonymize the programmers. And the features that we are talking about are, for example, once the binary is disassembled, we have assembly features, and we take assembly token bigrams or 2 consecutive lines and so on. And from syntactic features, again from the abstract syntax tree, we are taking node bigrams or the average depth of a certain node and so on. And from control flow graphs, we have similar features to abstract syntax trees, and once we extract all of these, we have a lot of features that we are dealing with. And for that, when we are applying dimensionality reduction, the first thing we do is apply the information gain criterion so that we take features out of these 700,000 features that reduce the entropy when they are taken out of the feature set. And then we are left with 2,000 features that keep the accuracy at its highest, and it's most representative of the coding style in binaries. But again, if I want to understand where code is in binaries, I won't be able to see this from 2,000 very low-level features that don't really mean much when you first take a look at them. And for that, I also apply correlation-based feature selection, which is taking the features that have the highest interclass correlation, which means that for an author, it has the highest correlation, but it has the lowest intercorrelation with other programmers. And it becomes the most identifying for individual programmers. And I'm left with about 50 features. Now I can get a better understanding of what might be representing coding style or in binaries. And when I try to analyze these 50 features, even though they are very low level, we still get low level properties that are representative of style that remain in binaries. And we have things such as arithmetic or logic operations, stack operations, as well as file input operations, and variable declarations and initializations. And these are not very trivial to basically refactor or change to hide your coding style. Okay, we said that we have a controlled environment. We take code samples from Google Code Jam and then compile it. And the reason for doing this was so that we can control for optimizations which might affect the de-anonymization accuracy or the anonymity of these samples. And when I take 100 programmers and I apply no optimizations when compiling, I get 96% accuracy, again with 9 samples with 9-fold cross-validation. And when I apply optimizations and then as well as stripping symbols, the accuracy keeps decreasing. With optimizations, it's not affected a lot. It drops to 89% accuracy, but with strip symbols, the accuracy is affected more. But again, here we see that the strip symbols, we have 72% accuracy, but the random chance of correctly identifying these programmers is 1%. So even stripping symbols is not anonymizing these people. Okay, what kind of obfuscations can I apply to anonymize myself in an automated way? And for that, I used an open source project, OpenLLVM, and applied 3 different types of obfuscations. First of all, bogus control flow insertion, where code will never reach that. but it's still in the binary, so it looks like a feature. But if I substitute instructions with equivalent instructions, making the codes shorter or more complicated and so on, or flatten the control flow to mess with the control flow features. And we see that obfuscations are decreasing the accuracy to 88% from 96 for 100 programmers. And again, this is showing that such obfuscations are not sufficient to hide coding style. Even in binaries, coding style remains after many transformations, compilations, or obfuscations. What happens if we try to increase our class size and we have 600 programmers? We see that with 20 programmers having 99% accuracy in correctly de-anonymizing them, with 600 programmers we get 83% accuracy, where the random chance of correctly identifying these people is less than 0.2%. And we see that the accuracy degrades gracefully in this case. Okay, what about real-world cases? This was a very controlled environment, Google Code Jam. People are implementing the source code, the functionality in a limited amount of time, and it's small snippets of code and so on. For that, first of all, I parsed GitHub repositories and ended up taking a bunch of code from hundreds of programmers. And after that, I compiled those, and many of them did not compile. And GitHub repositories are work in progress, so that's okay, but it took me days. I'm left with 50 GitHub programmers and able to de-anonymize them with 65% accuracy. Okay, this is one real-world scenario. What about malicious programmers? I'm currently actively working on that, but one case study I had in a published paper was with 6 malicious programmers and 10 samples. Some of these samples came from the hacker forum, null.io forum, and once the forum was leaked, I was able to find some live links to malicious code that they were selling and providing to their customers, and I was able to download those and find the ones that was relevant to my training set and reverse engineer it to get the features, as well as some malware authors from security reports and so on. And please, if you have a data set with known authors of malware, or if you have good automated methods for quickly reversing malware or malicious software or encrypted or packed or so on, anything that can help it, please come and talk to us after the talk. And we see that with these 6 malicious programmers, we have 100% accuracy, but I would like to make this experiment much larger scale, and for that, you need help with the data set. And now I will leave it to Rachel so that she can talk about more fascinating details about programmer de-anonymization.
A bit deeper onto programmer de-anonymization on GitHub. When we did this experiment, we got much lower accuracy than in the original Google Code Jam dataset. And with the experiments I'm going to show over the next couple slides, I think a lot of this comes down to the fact that a lot of these repos, we only had like a couple of files per author. And it turns out that this sort of, I think that's the thing that matters the most. There is a lot of noise where sometimes people will like link in other things and so on. But I think one of the biggest issues is that when you only have like 2 files to train on, or 1 file in this case and 1 to test, as opposed to the 9 files that we use for our experiments, I think that makes a big difference. So we've been, up till now, we've only talked about situations where people are writing code individually on their own. So most people probably don't actually code that way in real life most of the time. Most code is collaborative. So when we started presenting the initial work, we had a couple tweets about it. Halvar, who some of you might know, said, "I'll believe that this code stylometry stuff works when it can be shown to work on big commit GitHub histories instead of the Google Code Jam datasets." And Zuko talked about hearing from an intern at Apple that they disallow her from contributing to open source on her own time. And so we were interested from this like perspective, both of privacy Like if I want to contribute to something and I want to know if that particular commit is going to cause me problems later, and also just, to validate this stuff more in the real world, we wanted to do some experiments. So in this case, right, we're only carrying maybe who wrote a small piece of code, or we want to de-anonymize some pseudonymous account on GitHub who we have like several snippets or segments of code, right? So we don't have these whole files nicely written. And in this case, we're using the same feature set that we used before. We're trimming it down to about 3,400 features, so like quite a bit more than Aylin was using earlier on, but these are very small segments and snippets, so sometimes we need more features for that. And ultimately when we were doing this, we get about 73% accuracy at identifying the author when we're talking about 100 programmers for a snippet of code that's about 5 lines long. So we're interested in kind of understanding when this works and when this doesn't work. So what we did was we built this calibration curve. And what that does is it just shows us, like, in general, what the confidence of the classifier is relative to its accuracy for individual samples. And we can see that in some cases we have pretty high confidence, and in a lot of cases we don't have such high confidence. So this can help us understand, even though we have 73% accuracy, we can say, given this answer that the attribution has given us, should we believe it or not based on this confidence? And then we can know, if we know it with high confidence, we have much better belief that this is actually the programmer that we're looking for. And we're also interested in how long these snippets need to be and how many snippets you need to train on in order to get good results. So here's an interesting we have this sort of curve that happens where, so say we have fairly large snippets that are 38 lines of code. In general, with the Google CodeJam data that we were talking about before, they were about 70 lines of code, the files. But in this case, we only have 4 samples for each author or programmer, right? And this gives us about 54% accuracy on 90 programmers. But even if we have smaller samples, but much more of them, typically our result goes up. So even when we're only looking at single lines of code, and I'm a little nervous about this result because it's really preliminary, but if we have 150 samples to train on, we can usually identify the author about 75% of the time. So we're still trying to kind of understand what makes lines of code more attributable or not. I mean, certain lines of code are going to be pretty generic, but other ones not so much. But what happens when we want to identify accounts, not necessarily individual commits, right? This actually works a lot better, because what happens here is that the errors aren't correlated. So we get close to about 100% accuracy if we have 4 snippets, meaning the way that we analyze this is we ran git blame on these repositories, right? So that's how we get the repository clicked into snippets. And it turns out that the errors, the 73%, are typically not that correlated. So if we try multiple times and then we vote, our results get close to 100%. Not perfect. And so you can see this sort of heat map here, where the red area is basically over 90% accuracy, and it tends to happen once you end up having more than about 9 samples and more than about 5 snippets to train on, right? Or to test on. So once you have a certain amount of training data and a certain amount of testing data, meaning the account that you're wondering about has committed, more than 4 or 5 times, then your results get pretty good. Interestingly, we were also, one of the other things we tried was, instead of saying, okay, we're going to identify these little snippets individually and then vote, what if we merge them all to make a big sample? And it turns out that's better than the initial snippets, but it's not as good as doing them sort of one at a time and averaging, because then the errors tend to get compounded in a single merged thing. Okay, now for something a little bit different. I'm going to talk about deep learning because it's the new hotness. And so we talked about in one of the things that's sort of novel about this work is using the abstract syntax tree. In the past, most people had just used lexical and layout features, and sort of they've been doing this sort of code attribution stuff since the 70s, but it tended to get around 80% accuracy and not scale above like 30 programmers or so. So using these AST type features allowed us to get good results. But the thing is, an AST itself is not a feature, right? A tree is not a feature. You can't just feed this into a random forest and have it, tell you who it is. We manually chose these features, as Aylin has mentioned. We chose unigrams and bigrams and def. And so these tend to give us like very local features and very global features. But what we want actually is the ability to get maybe more nuanced features than that. So enter like a deep neural net, so we're going to try and automatically learn a new feature representation. So what we do is we first map the AST nodes into a vector, and we just use this embedding layer to do that. And then we create these subtree layers, and they're going to be using LASTMs or bidirectional LSTMs in order to learn new structures of the AST, and then we have a softmax layer to actually do the classification. So, little bit of background on LSTMs if you've not learned too much about them. So we have our neural net here on the right. It's an RNN, which basically allows us to handle sequential input and actually have some memory to be able to remember information. That's where those little feedback loops are. And an LSTM actually adds memory cells to this to have sort of more useful memory, again, so we can not just have super local features. So these cells have gates in them, and they ask sort of, what should I remember of this information that's going in? What should I just ignore? And what should I forget that we've already learned, so that we can, over time, develop a richer representation of the AST. So in this case, we're only trying to use the AST features. We're not using any of the layout or lexical features, and that's why these results for the random forest are lower than what Aylin showed. But you can see and this is using Python and C++, that we get, 86% accuracy on 25 programmers, or 73% accuracy on 70 programmers in Python, again, just using the AST, so this layout and lexical stuff matters too. But when we use our new AST features, we do get a big jump here. And so this new feature representation does seem helpful. And it's nice to have a sort of a sole AST representation, because it does allow us to, as we mentioned before, it's much harder to obfuscate, it's easy to port, and so on. So this allows us to learn better ASTs without doing this manual feature engineering, and it's language independent. And in our future work, we'd like to actually combine these features that have been learned with the random forest and fuller feature set to see if we get better results, or if this just overlaps with some of the stuff that we're learning from the layout and lexical features. Okay, so what about other languages? As I mentioned, basically porting this to a new language requires an AST parser, which exists for almost everything, and lexical and layout features that you choose for the language. So far we've done things for C++, C, Python, and JavaScript, and we get similar accuracy so far on the Google CodeGem dataset. The results with just using the AST tend to vary more, which is kind of interesting. One of the holy grail kind of applications of this would be able to sort of train on one language and test on another language. And we don't know currently, like, how much does your programming style change when you actually change languages? So to do this, we need some sort of universal intermediate AST representation, or some sort of just pairwise, porting between two languages. There is a project to work on this. It's like the Babelfish project, but it doesn't really appear like ready yet for this kind of application. It's something we're planning to look into a little bit. If people know about sort of generic AST representations, that'd be another thing we'd love to get your feedback on. So I'm going to end the talk with a couple interesting sort of software engineering insights that we've gathered as we've done this work about like what makes programming unique, which I think is kind of fun. So in general, we started with looking at attributing groups of people. So there's another programming contest called the Code Forces contest, which has a team competition, and the teams can compete on sets of problems. we have very preliminary results with 118 teams with about 20 submissions each. And they get about 67% accuracy. Now, I think this is one of the hardest cases for group attribution because the way that Codeforces works is it gives you a big group of problems to work on as a team together. So I think people are mostly splitting those up. So it's not actually group coding. So I'm kind of surprised that it even works as well as it does at identifying the team. So in the future, we'd like to work, again, with some more code repositories to get a better sense of like stuff that we know and can control for how much collaboration actually went into it. Difficult versus easy tasks. It turns out that implementing harder functionality makes programming style more unique. So when you're solving, and we can kind of control for this because the problems in the programming contest are supposed to get harder as they move on. So if we look at the same set of 62 programmers solving 7 easy problems, we get 90% accuracy, which is pretty good. But when we look at the same set solving 7 harder problems, the accuracy goes up to 95%. So that tends to matter. Also, programmer skill matters. So programmers who got further in the contest, which is some measure of skill perhaps, were easier to attribute. So in general, like the coders that advanced less far, we got 80% accuracy on them again, these are on the easy problems because they did that much. But then when we look even on the easy problems at the people who got further in the competition, we're able to classify them with 95% accuracy. So it's kind of interesting that as you develop programming skill, your style tends to be more unique. We're also interested in how coding style changes over time. So we looked at, again, this competition where people are training and testing are competing in both 2012 and 2014. So when we train on 2012 and we test on 2014, the accuracy goes down from 92% on this 2012 set to 88% when we test on the 2014 set. So it's a little bit of a drop. I'd be more interested in maybe looking at like when we look at even larger timescales than that, or sort of particularly formative sort of years, maybe like university and things like that, and how it affects people's programming style. Lastly, we're interested in coding style by country, right? So one of the things that this contest does is it has contestants from all over the world. So when we were porting this to JavaScript, we grabbed a bunch of JavaScript files, 84 files written by programmers in Canada and then programmers in China. And we were interested in just a binary classification, whether we could tell whether the file had been written by a Canadian or a Chinese programmer. Now this we expected to be like particularly easy because there's like a native language difference which may show up in things like variable names and so on. And in fact it worked pretty well. So it was 91.9% accuracy for this task. In the future we're planning to look at much larger set of countries and a much larger sort of set of files and see about sort of if there's actually kind of, if this is a native language effect or maybe sort of an education system style culture effect and what's going on there. But I think it'll be interesting. So in future applications, as we said, we're really interested in whether this actually works to find malicious code authors and also, what sort of anonymous contributors have to worry about when they contribute code online. We're interested in breaking this stuff. So writing better obfuscators. All the obfuscators we've tried so far have not been really targeted specifically to the AST. So we think that can happen. There was some research done at the University of Washington building on our work showing that people can kind of imitate other people's style when they're given that as a task to some extent. So that's, there's hope, right? Don't leave here thinking you can't ever write anonymous code again, but be careful. And in particular, like if you're going to contribute to a repository anonymously, you might want to create a new account for each commit, even though that's annoying. To find authors who write vulnerable code, we're interested in looking at source code and understanding kind of what software engineering type stylistic features lead to vulnerabilities. And also, some people have talked to us about finding out who to recruit directly by looking at how unique their coding style is and whether that suggests something about their programmer skill. So this was not work done just by Aylin and myself alone. I have lots of students and other collaborators at Drexel University and at Princeton and at the Army Research Lab and at Göttingen in Germany, who have all worked on various aspects of this project. So thanks to Bandar, Edwin, Rich, Andrew, Spiros, Arvind, Frederica, Masfikar, Dennis, Conrad, Greg, Claire, Mike, and Fabian for all of their contributions to this work. This is our contact information, our code to do all of this stuff. So if you actually want to try and figure out who Satoshi Nakamoto is and have a actual suspect set, you're welcome to try that. It's not something that we're going to do. We respect privacy. So, but the code is out there, and we have, I think, about 4-ish minutes for questions. So if people have some questions, we would love to take them. And then after the talk, we'll walk out the back and you can ask any more questions that you have. Thanks.
Hey, it's me, Cameron Salmon. Please like and subscribe if you enjoyed this video or learned something. Comment below if you want me to continue making these types of videos.